Buonasera, credo che possiamo cominciare la seconda lezione del professor Haroche. Ho già detto, però sono già state prese, quindi c'erano una serie di copie qua della presentazione di oggi, che peraltro è sul sito, le avete ritirate bene, quindi prego.
Okay, so thank you. So this is the second lecture in this series of lectures about the history of light. Last week, I have described how this story began in the 17th century with great discoveries which were linked with the invention of new instruments, the telescope and the pendulum clock. And I showed how these two instruments made possible to measure for the first time the velocity of light. I also emphasized the fact that optics was strongly related to other fields of science like astronomy, the science of navigation, earth sciences, mechanics, and also the importance of mathematics to express in mathematical terms the theory of the phenomena which were observed. I also emphasized the fact that the nature of light was in question. There were two theories which were opposed to each other. One by Huygens, which assumes that light was made of waves which propagated in a material medium with a velocity smaller than the velocity of light. And the other by Newton, which said that light was a flow of particles which propagated faster in a medium than in air. And of course, at that time, there was no way to decide between these two theories, these two models, because there was no way to measure the velocity of light in a transparent medium. So we had to wait until the beginning of the 19th century to resolve this problem and to find who was right between Newton and Huygens. And so this is the topic of today's lecture. I will be talking about the science of light during the 19th century. And I call this lecture the triumph of the wave theory of light, because as we will see, this is a theory which happened to be the true one. So the lecture will be divided into two parts. In the first part, I will describe what happened at the beginning of 19th century. I will talk about Thomas Young, who demonstrated by simple interference and diffraction experiments that light is a wave phenomenon, which is proving Huygens right and Newton wrong about that. Young has introduced the notion of wavelengths and has related it to the color of light. After Young, Fresnel in France gave to the wave theory a solid interpretation, he introduced the notion of phase of light and established that light has a transverse polarization. It's a vibration which vibrates in a plane which is perpendicular to the propagation of the light rays. Fresnel was also able to describe light propagation in anisotropic media, and he has discovered what is circular polarization. Finally, the proof of the wave theory was finally given by the measurement of velocity of light in water by Foucault in the mid-19th century, and he found indeed that the propagation, the velocity of light propagation was smaller in water than it is in air. The second part of the lecture will discuss the merging between optics, electricity, and magnetism. At the end of the 18th century and the beginning of the 19th, discoveries about electricity and magnetism accelerated. Coulomb discovered the law of electrostatics. Volta invented the battery. Ørsted observed the magnetic forces produced by currents, which were studied in details by Ampere. Faraday showed how the variation of a magnetic field produces currents in an electric circuit and found the laws of induction. He also introduced the notion of electric and magnetic fields. And this line of research has, of course, culminated in the 1860s by Maxwell theory, who established that electric and magnetic field propagated in space at a velocity which was found equal to the velocity of light. So there was a unification which shows that light is an electromagnetic phenomenon. And this unification of optics, electricity, and magnetism was a revolution in basic science. as well as for industry and communications, of course. But this discovery raised other questions at the end of the 19th century, which led to relativity and quantum physics. So I would try to cover this period going from the beginning of the 19th century to the beginning of the 20th century. And the story starts with Thomas Young. Thomas Young was a child prodigy. It is said that he knew how to read at the age of 2.5 years old. He spoke Latin and Greek. He was interested in medicine. In fact, he was a medical doctor. He was also interested in humanities. He contributed to the deciphering of the hieroglyphs, which were, this work was completed by Champollion in the 1820s, but Young contributed to that. But for our story, Young is important because he made fundamental experiment on the interference of light. He demonstrated that light is a wave phenomenon. He introduced the notion of wavelengths, which is a distance between two crests of this wave, and the notion of light frequency, which correspond to the number of undulations that light makes in 1 second. And he has explained that colors are, of course, related to the wavelengths of light, which was a mystery since the first study of colors by Newton. I quote here this sentence by Young because it defines very well what modern science is about. This is the first sentence of a Bakerian lecture that he gave in 1801 to discuss the nature of light. He said, he started by saying that the invention of plausible hypotheses, independent of any connection with experiments, can be of very little use in the promotion of natural knowledge. What he means there is that, for instance, the hypotheses which were made during antiquity, which were not based on experiments, were maybe interesting at the poetic level, but had no value for science. And he goes on saying, the discovery of simple uniform principles by which a great number of apparently heterogeneous phenomena are reduced to coherent and universal laws must ever be allowed to be of considerable importance towards the improvement of the human intellect. So this means that a scientific theory should be based on observation. It should lead to theoretical models which unify observation and make new predictions. It's exactly what he did. He published his result, his theory, in a general course of physics, in which he does not only talk about light, but summarized all the knowledge about physics, which was known at the beginning of the 19th century. So about light, he observed for the first time interference effect, and he performed the famous double slit experiment that everybody knows about. So you have a source of light which shines on a screen in which you have two small holes, two small slits, and the light which shines through the slits interferes. The beams coming from the two spots superpose, and when there is a difference, a path difference corresponding to an integral number of wavelengths, the light is reinforced and you have bright fringes. And when the difference is equal to an odd number of half wavelengths, the two waves are in phase opposition. The maximum of one wave corresponds to the minimum of the other. They cancel each other, and you get this picture of fringes, which Young compared with what you observe at the surface of a pond when you have two plungers which produce waves at two different points. So I don't want to tell more about that, but I show you on this slide, and I give you at the bottom of the slide the address of an internet site on YouTube in which you can see a very beautiful demonstration of Young double slit, which is a very simple experiment, which is made with a big cardboard box on which you have made very two narrow slits on one edge of the card box. And when you look inside, you see these beautiful fringes. They are colored because interference condition depends, of course, on wavelengths. So if you use, as it was done on a beach, the light from the sun, which is white light, you get this kind of colors. And on this video, you see how you can compare that with the waves that you can produce on the surface of the water of a pond. So it's a very clever demonstration of Young double slit experiment, which shows that the experiment involves very, very simple apparatus. Young also observed the fringes, the diffraction fringes, which are obtained when you send white light on a very narrow wire. And you see here the picture, the wire is comprised between these two dotted lines, and you see a lot of fringes inside the shadow and outside the shadow, which are colored because of the same reason as I said before, because it's illuminated with white light. He also observed Newton rings. He put a lens on the surface of a plane, and he see rings which correspond to positive and negative interferences. You have to compare the wavelengths of the light with the separation between the spherical diopter and the plane. And from the measurement of this separation, he was able to deduce for the first time the value of the wavelengths of light. And it is shown on this table that Young published in his article. And you see for the first time the value of the wavelengths of light, lambda, from red to blue. And you see the measurement is in tens of thousands of 1 inch, very, very small values. We know now that this corresponds to widths which are between 0.4 and 0.7 micrometer. And from these values, knowing the velocity of light, which was obtained by Bradley, I discussed that last week, he was able to deduce a number of undulation per second, which is just the frequency of light. And he found this tremendously large number. You see for red light, he found 460 millions of undulation per second, which correspond in modern notation to something like 400 terahertz. That is 4.6 10 to the 14 hertz. So these are huge frequencies, which were absolutely impossible to measure at that time, but Young was able to say this is a frequency of light. And in the first lecture, I gave you an example. I talked about optical clocks. In fact, the optical clocks, which measure time with a fantastic precision now, are precisely counting this kind of frequencies. So, but it took 2 centuries since the time of Young to be able really to count these frequencies and to use them in a practical device, which is the modern optical clock. Of course, lambda and nu are related by the fact that the product of these two quantities is just the velocity of light. Young also discovered the properties of gratings. He said that if you trace lines, very closely spaced lines on a piece of metal or a piece of glass, and if you send light on this, you separate the different wavelengths of light. And you can do this experiment very easily now, for example, with a CD or a DVD disc, because there are grooves on the disc which are here for lasers to be able to read them. And if you send white light on this kind of CD or DVD disc, you get this spectrum of colors. In fact, these gratings were also developed about at the same time by the German Fraunhofer, who built gratings with a different technique. What he uses, he had very narrow wires, and he set these wires parallel to each other by rolling them on a screw. And with these gratings, he was able to scatter the light of the sun to get a spectrum. And he observed on the spectrum very narrow dark lines, which were due to the absorption of atoms in the atmosphere of the sun. So these are the first atomic spectra dating from the beginning of the 19th century, which shows the progress made in optics at that time. So what are the questions which are left unanswered by Young? First of all, he did not discuss the direction of the vibration. Is this vibration a longitudinal vibration like sound or a transverse vibration? This question remains. Young's theory also remains semi-qualitative. He did not give a precise calculation of the diffraction fringes, and he also did not give any estimate of the fraction of light which is reflected or refracted inside a medium when the light enters into a material medium. He also, of course, had no idea of how light interacts with matter. Light is a very, very fast phenomenon occurring on the very short distances. And of course, in order to understand what happens, you have to have a microscopic description of matter, which was not available at that time. Finally, he did not discuss the nature of the medium in which light propagates in empty space. This ether, which was introduced by Descartes and Huygens, and which are still mysterious. So the answers to the first question here were soon given by Fresnel and Malus and Arago, the French school of optics. But the last two questions had to wait until the end of the century and the beginning of the following century. So let's start now. Let's discuss now what happened in France at the same time. Malus was an engineer who had participated to the Egyptian campaign of Bonaparte and was in Paris beginning of the 19th century, discovered the phenomenon of polarization of light. He is supposed to have observed that by looking at the light which was reflected on the windows of the Luxembourg Palace in Paris. He was living in the street and he saw the sunlight reflected, and he had the idea to look at this sunlight through his Icelandic spas crystal, this crystal which was studied by Huygens in this 18th century. And he found that the reflected light intensity was changing when he turned this crystal. And he discovered the fact that light had a property which was not symmetrical by rotation around the ray of light. And this is known as polarization. But at that time, Newton was considered to be the person who was right. And he tried to interpret this with the particle theory, assuming that the particles of light, the molecules of light, as he called them, had some kind of anisotropy, which explained this property. But the particle theory was absolutely unable to explain quantitatively what was going on. And the explanation was finally given within the wave theory by Fresnel, as I will discuss in a moment. So this is the experiment performed by Malus. On this slide, I show you first what Huygens had done in the 17th century. He had two crystals, and as we have seen, when the light is going through one crystal, the light ray is split into two parts, an ordinary ray, which I have shown here in blue, which goes straight, and then extraordinary ray, which is displaced laterally, which I have shown you in red. Now, if the two crystals are oriented in the same way, you see that the ordinary ray, the first crystal goes on as the ordinary ray in the second one. But if you turn the second crystal by 90 degrees, you see that the ordinary ray of the first crystal becomes the extraordinary ray of the second one. And this is a property of polarization. What Malus did is to perform exactly the same experiment, but instead of analyzing the light, instead of producing the light by a first crystal, he produced this light by reflection on a piece of glass or on a mirror. And what he observed is that the light reflected has the same property. The light which goes through, which has been reflected, which goes through the analyzing spas crystal, is going either along the ordinary ray or along the extraordinary ray, depending upon the angle of rotation of this analyzer. And he found that the intensity of light which is transmitted in the ordinary ray varies as the cosine square of this angle. This is called the Malus law. And this shows quantitatively how light is being transmitted. In fact, this effect is only partial if the incidence angle is not very peculiar. This property of polarization becomes 100% if you are at what is called Brewster angle. Brewster was an English physicist who did experiments on that. Brewster angle is the angle for which, as you see here, the reflected beam and the transmitted beam are at right angle from each other. And when you are at this angle, the light which is reflected is 100% polarized. In fact, as Fresnel had shown later, it corresponds to a vibration which is parallel to the surface of the mirror. And this is a property which is used, for instance, when you have glasses to avoid reflection from water. You put the polarization of your glasses in such a way that they don't transmit this parallel polarization. So this was the discovery of the polarization of light. And now it brings me to Fresnel, who was really the father of modern optics. Fresnel was a French physicist who completed, in fact, the semi-qualitative work of Young. He was not aware of Young's work. It was during the Napoleonic Wars, and France and England were separated. There was no communication for some time. And what Fresnel did was to realize various versions of double slit experiment apparently without knowing about Young's work. He showed that the Huygens principle of secondary waves could be put into a full quantitative theory. And so he developed this principle by using advanced mathematical models, which allowed him to calculate with precision the intensity of light diffracted by various obstacles. He showed also that light makes very clear shadows, which Newton did not believe. Newton said that the wave theory ought to be wrong because light should be able to get into obscure parts and would not propagate along straight rays if it was not made of particles. And Fresnel proved that was wrong. He also provided a simple and quantitative interpretation of Malus experiments. And he explained all the properties of birefringence, all the properties of these crystals which propagate two light beams out of a single incident beam. He also discovered the circular polarization of light, the fact that light can be polarized in such a way that the vibration is propagating and rotating like a corkscrew, and it's a circular polarization. And finally, he introduced a theoretical description of interference phenomena, which is based on a geometrical representation of the wave vibration in an abstract plane, which is called the Fresnel plane, and which is in fact nothing else than the plane of complex numbers in mathematics. In this way, he showed for the first time the usefulness of complex number analysis to describe periodic physical phenomena. And he pointed also to the importance of the superposition principle, which will play later an essential role in all of physics. I show you here two examples of interference experiment, various versions of the Young double slit. He did one with, he used a mirror, two mirrors which make a very small angle so that it reflects the light from a source as if it was coming from two images very closely spaced. The light from these images interfere in a place where the two beams superimpose, and then he saw fringes here. So it looks exactly like the Young double slit, except for the fact that there are not two small holes, but two very closely spaced images. In fact, he did these experiments at a very difficult time of the history of France. It was during the 100 days corresponding to the return of Napoleon from Elba, just before Waterloo. And Fresnel was politically against Napoleon. He was a royalist, and so he had to escape from Paris. And he went into a farmhouse in Normandy, and he did his experiment in the kitchen of the farmhouse with a very simple equipment. In fact, one says that he did not have a lens to concentrate the light from the sun, so he used a drop of honey as a very simple lens, and he did his experiment on with very simple equipment. So this is the Fresnel mirrors. He did a similar experiment using what is called a biprism. You take two prisms which you glue on one face, and again you get from a single source, you get two images, S1 and S2, and you get interference fringes in the superposition of the two beams. As always, to get these interferences, you need to start from a single source to split it into two parts and to recombine the parts. And I will come back to this in a moment. He also did very, very precise calculation. You see here, this figure is taken from Fresnel treatise in optics. He looks at the light coming from the source here which is here blocked by a screen, a half-plane screen, with a very sharp edge. It's a kind of razor blade which stops the light here. And he calculated the distribution of light intensity you should see downstream on a screen. And you see he used the Haroche's principle. On the wave front, which is not blocked here, he assumed that you had secondary sources, each of these sources radiating forward a partial wave. And he looked at the interference of all these partial waves at different points on the screen. And you see here his theory. These are the fringes that he calculated, and superimposed, you see the fringes that you observe now with the laser light. In fact, the light he had at that time was not monochromatic enough, and he could not see this. But with laser light of a single color, you can reproduce exactly the result obtained by Fresnel at that time. And you see the important result here is that you see, this is the point where the screen blocks the light. You see that there is a little bit of light which is leaking into the shadow, and that you have a lot of shadows, fringes in the part where light can go in. But in spite of that, you see indeed that you have a quite clear separation between the shadow and the light, which was a proof that light propagates in spite of this diffraction effect. The first approximation is that light is really blocked by screens, which was something that Newton did not believe in. So this was the calculation of Fresnel, very precise calculation of diffraction using the Haroche's Fresnel principle. He did also a very dramatic experiment. People believe, the people in the French Academy of Sciences believed in Newton and not in Haroche. And in particular, the mathematician Siméon Poisson had challenged Fresnel. He said, okay, if you send light on a disk at the center of the shadow, according to your theory, you should have a bright spot. Why? Because all the secondary sources which are around should interfere positively at this point because of symmetry. So you should have a bright spot in the middle of the shadow, which is ridiculous, which means that your theory is wrong. So Arago was a friend of Fresnel, set up the experiment on a table in front of the academy, and you see that there is indeed a bright spot in the center of the shadow. So it's called now the Poisson spot, in spite of the fact that Poisson did not believe in it. And the legend says that it is the point at which the wave theory of light became accepted. Fresnel also gave a very clear description of polarization. He said that the light vector, the vibration of the ether which produces light, is oscillating in a plane normal to the light ray propagation. This is polarized light. Now, the natural light from the sun is not polarized. What does it mean? According to Fresnel, it meant that, in fact, the polarization was changing randomly very fast in time. And so you had all the polarization. And when you sent light on a mirror or through a sparse crystal, one of these polarization was selected. And this is what he called polarization. This also explains why, to see interference effects, you need to start from a single source, split it in two parts, and recombine. Why? Because the unpolarized light would not give rise to interference if you take two sources, because the two rays would be randomly polarized. Whereas if you start from a single one, when the polarized changes in one of the beam, it changes in the other in the same way, and so interference can occur. The coherence is preserved in spite of the fact that the polarization changes randomly. So this was a big step. Now, the step which was really the triumph of Fresnel theory is that he was able to explain completely the phenomenon of birefringence, the fact that a light beam going through an anisotropic medium gives rise to two beams, and he was able to compute all the properties of this. I try to give you an explanation here. This anisotropic medium has what is called an optical axis, an axis such that if the light vibrates along the axis, it propagates within the medium with a given velocity. On the other hand, if the light vibrates normal to this axis, it propagates with a different velocity. At that time, it was just difficult to explain. Now we know what happens. In fact, in these media, the electric charges which are in the media vibrate with a different restoring force according to one direction or the other. So you get different responses to the light excitation, which explains that you have different velocities of light in the medium. So assuming that, let's assume now that this picture is showing what happens in a plane which is defined by a normal to the incoming diopter. So the blue line on top is normal to the entrance diopter of the medium, and the optical axis red. These two lines define the entrance, the plane in which I will discuss. So what happens if you polarize the light normal to this plane? If the polarization is normal to this plane, it is of course normal to the optical axis. And so the light which is polarized perpendicular to the plane of the figure will propagate with the same velocity, whatever the direction. So for this beam, the ordinary laws of optics apply. The secondary waves that you have at the surface to describe the propagation are spherical waves. The envelope gives this plane wave, and you get into the medium as if the medium was isotropic. What happens now at the bottom for the light which is polarized in the plane? Obviously, this light has two components. One component of the polarization is along the optical axis, and another component is normal to the optical axis. So the light in the medium propagates with two different velocities depending upon its direction. What does it mean? It means that the secondary waves are no longer spherical, because depending upon the direction, light propagates at different velocities. So these secondary waves are not ellipsoids. The surface are ellipsoids, and the envelope of these ellipsoids, the contact with the ellipsoids is no longer in the same direction. It goes at an angle, and it explains why the light enters in the medium at an angle, as is shown at the bottom. And of course, when light gets out, it is polarized. The light beam which has been translated is polarized orthogonal to the light beam, which is going straight. These are the properties of this birefringent media. And you see that Fresnel was able to explain that in a quantitative way. Now, another important point that I want to make about Fresnel is that he described the properties of light in what he called what is now called the Fresnel plane. It's an abstract plane in which you can represent a vibration by a circle, by a motion on a circle. Consider a linear vibration, the fact that the vibration of the light field goes back and forth along a line. This is something that you can observe if you have, for example, a bicycle wheel, and you look from the top, and you suppose that you attach a ball on one of the spokes of the wheel. If you look on the top, you see this ball going back and forth according to a linear motion. Now, if you look at the same wheel on the side, in fact, it's rotating, and the angle which the spoke makes, for example, with the horizontal, is called the phase. And you see that when the tip of this light vibration is making one back and forth motion, the ball makes one turn, and the phase increases by 2 pi radian, by an angle of 2 pi. So you can define in this way the phase of the field, and of course, this phase accumulates with time at a rate 2 pi nu. If you have nu, which is the frequency oscillation per second, the angle increases by 2 pi nu, and omega is called the angular velocity of this phase. So this is this seems like just a change of notation, but it's very important because in fact it introduced complex numbers into physics, because this Fresnel plane is nothing but the complex plane of mathematicians. One direction is just the real axis, The other direction is imaginary axis. And the vector which represents the vibration is just a C number whose phase evolves by 2 pi each time that the motion makes one turn. This is very useful to compute interference phenomena. For instance, I have shown here what happens when you have to combine two light beams which have been separated and recombined. What happens when they are in phase? When they are in phase, the vector which represents the total vibration is the sum of the two vectors, which is twice as large. Now, if they are out of phase, which happens here, they just cancel each other. And in between, you see that if you want to construct the resulting vector, you have to add geometrically the two vectors. And for that, you have just to translate one vector so that the origin of the second vector coincides with the tip of the first one, and you take the diagonal and you get the total vector. And mathematically, what you find is that the amplitude decreases as a sine or a cosine function from the maximum to 0, and it is the shape of the fringes that you get when you make an interference experiment. So in this way, he was able quantitatively to explain the shape of the interference fringes, how the intensity varies when you go from a bright to a dark fringe. He was also able to combine more than two waves. At the top, I show you three waves, which are 120 degrees out of phase with each other. The three vectors point along the direction of the summits of an equilateral triangle, and the sum of these three vectors is 0. So you see that if you have a fan of vectors which make regularly change by the same amount in angle, you find 0 when you sum them, and this is something which will be important in a moment. So he was able to explain all the interference effects in this way. This also is very interesting because it gives a clear interpretation of the Fermi principle of the shortest time for light to go from one point to the other. So assume that you have light, monochromatic light starting from point A, and you want to find the path which brings the light from A to B. And you do it using the Fresnel principle. That is, you take a surface here, and you say the light which comes here is the interference of all the sources on this surface, which you can compute because you know the path, all these passes, and you know the wavelengths. Now, for each of these points, you can do the same, starting from the surface, from the auxiliary sources on this surface and so on. And you see now that the field which is detected at point B is the sum of all kinds of zigzag passes going from A to B. All the passes are allowed, but what happens is that at the end, you have to sum all these vectors. And these vectors turn very fast in the Fresnel plane. As soon as you change a little bit the path, you accumulate a different phase because the time it takes for the light to go through this zigzag is different. And the only paths which will remain are the ones for which all these phases are at an extremum, either a minimum or a maximum, because then a small variation around this does not make all these passes different. In other words, it is as if on each pass you had a clock, which is the tip of this vector rotating very fast. You measure all these times, and the only times which matters are the one for which this time is extremum. This is exactly Fermat's principle. And this answers a very deep question that some people asked from the 18th century on, is how light knows this is the shortest path. And of course, light does not know anything. Light is a vibration, is a wave, and the wave explores everywhere. And only by constructive interference, the passes for which this passes is extremum count. So this is Fermat's principle. The last point I want to discuss briefly is circular polarization. What Fresnel did, he was able to cut a birefringent crystal with two planes which contain the optical axis. And you see, you have here the optical axis horizontal, and he sent in this, through this plate, a field which is polarized at 45 degrees from the optical axis. So what does it mean? It means that this field can be expanded into two components, one whose polarization is parallel to the optical axis and one which is orthogonal. And these two components propagate with different velocities inside the crystal. And so they accumulate different phases. And when you do the calculation, you find that the phase difference between the two components is 2 pi L, which is the width of the crystal, times the difference of indices and 1 minus n2 over lambda. And so what you get are the result of a vibration, which is a sum of two vibrations which have different phases. And when you do that, what do you find? Of course, it depends on the thickness. And for the thickness, which is called quarter wave plate, the difference is such that the two components are pi over 2 out of phase with each other, which means that if one component is like cosine omega t, the other one is like sine omega t. And of course, you know that if you combine a cosine with a sine, you have a rotation. You have the tip of the vector, which goes around on a circle. So he had been able to produce light, which behaves as a kind of corkscrew. The tip of the light vector is not only propagating like this, but it's also rotating as it propagates. And this is called circularly polarized light. And you can, of course, also make elliptically polarized light, all kinds of light, going from linear polarization to circular and back. This circular polarization carries angular momentum. And we'll see that in other lectures that it is an important property of light. So let me conclude by trying to state what are the achievements of Fresnel. First of all, he firmly established the wave theory of light, and he showed the validity of Huygens principle, allowing a precise calculation of diffraction phenomena. So with Huygens, it was a quite kind of semi-qualitative approach with Young too, but Fresnel used it to make precise calculations. He discovered the transverse polarization of light. He explained all birefringence phenomena and the possibility to give to light any kind of polarization, linear, circular, or elliptical. And he described ways to analyze this polarization. And this is really what makes people at the time of Fresnel believe in his theory, because people had tried many ways to explain this with a particle theory and were unable to give satisfactory explanations. His theory also allowed him to establish the formulas which gives a fraction of light. When you send light on a diopter, part of the light is reflected and part of the light is refracted inside the medium, but the fraction of light which were reflected and refracted were unknown until the formulas that Fresnel gave. And he showed in particular that for the Brewster angle, you get a total reflection of the polarization parallel to the surface. He introduced the Fresnel plane and the complex number representation of light vectors, which will be later generalized to probability amplitude in quantum physics. So it's a very important advance. His theory of light also illustrates a principle of wave superposition, which is based on the linearity of the wave equations, and this will be later confirmed by Maxwell, as we will see in a moment. And I want also to say that I emphasized last week the connection between blue sky research, which is what Fresnel did, and instruments. In fact, Fresnel spent part of his life to build new lenses called diffraction lenses, Fresnel lenses, which collected light much more efficiently, making big lens possible. And they were used in all lighthouses during all the 19th century and beginning of the 20th century. So he was also an engineer, and he spent a lot of his time not only doing basic research, but also doing applications. And it's amazing what he was able to do, because he died at the age of 35 or 36 years old after having really revolutionized optics. So now I come to the last question I want to address in this first part. There was one point which was still missing. Okay, if light is a wave, it has to go slower in a medium than in air. But nobody had measured the velocity of light in a medium, because the only measurement which were available at that time, the one of Bradley or the one of Romer in the 17th century, were astronomical determination. Of course, there is no way you can put water in a tube extending over the Earth's orbit. So it was impossible. And Arago, who was a friend of Fresnel, designed an experiment and said you should be able to measure the velocity of light in the lab now. And two friends, Fizeau and Foucault, decided to do that. And I will describe first the first experiment, which was successful, was Fizeau's experiment performed in 1850. And in fact, what Fizeau did is to take back the old idea of Galileo, but applied to it the technology of the 19th century, which was not possible in the 17th. So you remember what Galileo tried to do? He tried to measure the time it takes for light to go from one hill in Tuscany to another one and back. And Fizeau did that, but he was not in Tuscany, he was in Paris, and he used two hills in the Paris suburbs, Suresnes and Montmartre, which are separated by 8 kilometers. And instead of having an assistant which was uncovering his light when he saw it, which takes some delay, he just used a mirror. A mirror reflects instantaneously, does not think about it, just reflects light as soon as it received it. So the setup was as follows. You had a source of light here. I think it was a piece of chalk which was heated at a very high temperature. And the light fell on a beam splitter. Part of the light was going through. There was here a telescope which was transforming the light beam into a parallel ray of light so that the light was not diverging too much. And another telescope here in Montmartre was focusing the light on an eyepiece. And then it went on the mirror and came back on its way back to Suresnes. And here, when the light arrived, part of the light was sent through the beam splitter to an eyepiece, and Fizeau was looking through the eyepiece. So this is how it went. But now you have to interrupt the light, as Galileo was just using his hand to let the light in and out. What Fizeau did was to use here a gear wheel, a wheel which had holes, 700 holes. The wheel was rotating very fast. And so what he was looking for is the fact that for a given speed of the wheel, the time it takes for the light to go back and forth, one hole would be replaced by the tooth, the next tooth, and the light would be blocked. So he looked through the eyepiece and fixed the velocity to the value of rotation velocity, which blocked the beam coming back. And he said, he was able to compute the time it takes, of course, because he knew how fast the wheel was rotating. And this was the time it takes for the light to go the 17 kilometers from Suresnes to Montmartre and back. So it was a very clever experiment, and it gave a velocity of 315,000 kilometers per second, which is about 2 or 3% higher than the value found by Bradley. But it was the first value on Earth. And then Foucault entered into play, and Foucault did even better. Foucault decided to do the experiment in a lab in his house. And instead of 7 kilometers, he had only 7 meters. So how did Foucault did that? Foucault used a setup, which I show you here, which also has something rotating. But you see what happens is that the light is coming in and going here to a rotating mirror. Now, it's not a rotating wheel, it's a mirror which rotates very fast, a small mirror which makes 400 or 500 turns per second. And you see the mirror is sending light at some point to this mirror, at some point to that mirror. And then the light comes back and is reflected back here. And you have again a beam splitter, and you look through an eyepiece on the side. So what happens? Let's first look at what happens on the upper part of the setup. The light is going here, then coming back. But when the light comes back, the mirror has turned a little bit. And so the returning beam is rotated by twice the rotation angle of the mirror, which means that on the eyepiece here, you see a spot which is slightly displaced with respect to the spot which would be observed if the mirror was not turning. So this gives you the velocity of light, if you know exactly all the geometry. But the trick is that on the symmetrical part here, exactly the same thing happens, but now light is going through a tube containing water. And so when the light comes back, you have another spot which is more separated from the original one because light is going slower in water. So during the time the mirror turns, it takes more time for the mirror to turn while light is going back and forth, and the angle is larger. And so the trick here is that by comparing the position of the two spots, he gets directly the ratio of the velocity of light with respect to the velocity in air without having to know what this velocity is. And he found that light in water is going 1.3 times slower than in air. So this was the nail in the coffin of the particle theory of light. It was clear that Huygens was right and Newton was wrong. It was also the end of the friendship between Fizeau and Foucault, because Fizeau, when Fizeau learned that Foucault was going to do the experiment, he told Foucault, okay, we are trying to do the same experiment, so let's do it together. And Foucault said, no, I do it, and you do it on your side. And he was able to do it faster than Fizeau. And so from that point on, they were no longer friends. And this is a kind of story which happens in research still now, of course. Now, Foucault did something else. Foucault went on and he decided to measure the velocity of light with even more precision. And in order to win precision, you need to have a longer path. And of course, he cannot have a longer path in his lab. So he went in Paris Observatory, the place where Römer had made his observation. He used a big room. And in this big room, he placed many mirrors, something like 7 or 8 mirrors. So the light which was going from on the rotating mirror was sent on this path, making a path of about 80 meters before coming back. So he got a much larger angle when he did the experiment. In fact, when the light is coming back, it goes here. You have a beam splitter, he has a microscope and an eyepiece, and he's looking at the spots exactly in the same way as he did before. And the other trick is that in order to measure the frequency at which the mirror was rotating, he compared this rotation with the rotation of a gear wheel here, which was driven by a clock, by a very precise clock. And he did a kind of stroboscopic experiment. He compared the two velocities in this way and was able to measure with precision the velocity of his mirror. And then he got, from this experiment, he got a value for the velocity of light of 298,000 kilometers per second, which is within less than 1% or 0.5% of the value which is known today. Why did he do this experiment in an observatory? It's because the head of the observatory, Le Verrier, needed this value to measure with precision the astronomical unit. In fact, one knows that it takes 823 minutes for the light to go from the sun to the earth from astronomical measurements, but you need the value of the velocity of light to find this distance in absolute values. And he found the value of the astronomical unit, which is very precisely within less than 1/2 or 1/3 of a percent the value which is admitted today. So it was a measurement which was important for optics, for the theory of light, but also for astronomy. Now, the last experiment I want to talk about here is very interesting because it connects with what I will be telling you next week. It has a connection with relativity. In fact, Fizeau, which was beaten for the measurement of light in water, decided that there was still something which had to be done about the velocity of light in the material medium. What happens if the medium is moving? What is the velocity of light in a flow of water? Not in a water which is still, but in a flow of water. And this is important because it is related to the notion of ether. You know, the ether is supposed to be the medium in which light propagates, and the Earth is moving in the ether. So if the velocity of light has a given value in ether, it would have a different value in the reference frame of the Earth, which is moving. And at the end of the 19th century, we'll see that Michelson tried to do this experiment. But Fizeau, before that, tried to do an experiment at the smaller scale to find out if when a flow of water is moving, the velocity of light is different or not. And he did the first interferometric measurement of the velocity of light. You see the setup is shown here. You have a source of light. Here, a beam splitter, part of the light is sent here. And you have here a tube which has the shape of an U, and the water is flowing very fast from top to bottom. And you see that the light beam is separated in two passes. You have a green pass, which is going like that, and a blue pass, which is going in the opposite way. Because when the light is coming out here, you have here a mirror on the lens which refocuses the beam inside. If you look at this figure, you see that one beam is going along the flow, and the other beam is going against the flow. And if the light velocity is different for the two beams, you will have fringes which will be displaced, and you will see that the intensity seen by the eye of Fizeau would be different from maximum or minimum intensity, depending upon the difference of velocities in the two parts. And in fact, what he expected, and it means that the velocity of light in the medium, which has an index n, should be c over n minus v or c over n plus v if the flow was dragging the light. And if you subtract the two, you find this phase shift, which is proportional to n squared L over lambda. L is the length of the path, lambda is the wavelength, and you have an n square effect. And Fizeau was surprised because he did not observe that. What he observed is something which looks like n squared minus 1, so a much smaller effect. And he interprets that by saying that, in fact, the flow is partially dragging the light. But the real explanation is that you cannot combine a velocity close to the velocity of light with v, according to classical physics. You have to use relativity, and in fact, Einstein gave the explanation, and he knew about Fizeau experiment, and the fact that he was able, with the theory of relativity, to find exactly the result that Fizeau had found without understanding why, this gave to Einstein the feeling that he was on the right track. So it was a kind of, what Einstein did was a kind of post-diction of Fizeau's experiment, and this is something which we'll come back to next week. So at this point, I ended what I wanted to say about physics in the mid of the 19th century. So what was known at that time, just before Maxwell? It had been established that light is a transverse vibration whose wavelengths extend from 0.4 to 0.7 micrometer, from blue to red, oscillating at huge frequencies of millions of hundreds of hertz. It propagates in vacuum at a velocity close to 300,000 kilometers per second. Transparent media are characterized by an index which depends on frequency, and in anisotropic media upon the direction of light's polarization. And the velocity of light in matter is smaller than in vacuum, and its dependence on the wavelengths explains, of course, the dispersion of prism and gratings and the colors of thin plates. Interference and diffraction effects are explained by a principle of superposition implied by the Huygens secondary waves model, which is mathematically expressed in a formalism describing the wave amplitudes by complex numbers, which add up like vectors in an abstract space, finite plane. The attenuation of light, which I have not talking about that, but the attenuation of light in an absorbing medium was described by introducing the notion of a complex index, which has an imaginary part, and the characteristic length over which the light intensity decays is inversely proportional to the imaginary part of the index. I remind you that this attenuation, this exponential attenuation in medium, had been studied in the 18th century by Bouguer and Lambert, and it got now a more mathematical model. Some questions were still, of course, unresolved. What was the nature of light's vibration? It was assumed that it propagated in the ether, which is an hypothetical medium supposed to have very strange properties. It occupied all space in the universe. It permeated transparent solids and liquids and was able to transmit at a huge speed transverse vibrations. Other mysteries included the description of the mechanism by which matter interacts with light. And of course, this was before the discovery of the electron and the atom. And the connection between light and heat was also mysterious. It was well known that if light comes on a surface, it heats the surface, but why was not clear. Many of these mysteries were solved with the birth of electrodynamics and the recognition that light was an electromagnetic wave. And this would be the second part of this lecture. So I guess we could stop for 10 minutes now, and we resume at 5:10. Thank you.